For a long time, quantum physics seemed to belong only to the world of very small things. Electrons and other tiny particles behave in ways that feel strange compared to everyday life. One of the most surprising effects is called quantum tunneling. It means that a particle can sometimes pass through an energy barrier, even if it does not have enough energy to climb over it. In simple terms, it is as if something can go straight through a wall instead of bouncing back. In the normal world around us, this almost never happens. Large objects do not show clear quantum behavior because they constantly interact with their environment. Air, light, heat, and other particles disturb them. This process destroys delicate quantum states very quickly. As a result, quantum effects usually disappear when objects become bigger and heavier. A research team in Germany, working at Heidelberg University, has now pushed this boundary further. They studied a small group of 7 lithium atoms. First, they cooled the atoms to extremely low temperatures, very close to absolute zero. At this point, the atoms move extremely slowly and become easier to control. Then they place the atoms into a carefully designed optical lattice. This is a pattern made of light that can hold and organize particles like a grid of tiny traps. Inside this setup, the atoms formed a single connected cluster. Instead of behaving like separate objects, they acted together as one system. The researchers then created an energy barrier and observed what would happen when the cluster reached it. The result was surprising. The entire group of atoms crossed the barrier as one unit, even though their energy was not enough to overcome it in a classical way. During this process, the cluster behaved like a single quantum object. It existed in a state that can be described as being in 2 places at once. This is similar to the famous idea known as Schrödinger's cat, where a system can be in a combination of different states until it is measured. What makes this experiment important is not just the tunneling itself, but the size of the system. Instead of a single particle, a group of several atoms showed coordinated quantum behavior. This suggests that quantum effects can survive in more complex and larger systems than previously demonstrated in such clear form. Researchers are careful not to overstate what this means. It does not mean that large everyday objects like balls or people can suddenly pass through walls. The experiment required extreme conditions, including ultra-low temperatures and precise control of light fields. Without these conditions, the quantum state would quickly disappear. However, the results still open interesting possibilities. If scientists can control quantum behavior in larger systems, it may lead to new types of extremely sensitive measurement devices. These could improve how we measure gravity, time, and tiny changes in motion. In the future, such technology might help create navigation systems that do not rely on satellites and instead use internal physical references with extreme precision. For now, the experiment is another step in understanding how the quantum world connects to the world we see every day. It shows that the boundary between small and large is not absolute, and under the right conditions, even groups of atoms can behave in ways that once seemed impossible.